Okay, so welcome back to our session and our live stream. The second talk will be by Dave Kleinschmidt from Rutgers, and he's going to be talking about a formula for bridging the table matrix divide.
Great, thanks. So I'm going to talk about some work on developing a kind of supercharged formula language for Julia. The motivation for why this language exists is that most of the data that much of the data that we work with is tabular, so it comes in as columns with names that are heterogeneously typed, so each column might have a different type of data stored in it. But the problem is that many of the computational procedures you want to apply to this data require a numerical array of some sort. Right? So the question is, how do you bridge between these two formats? And of course, you can just sort of hand write your transformation every single time, but that's brittle and hard to extend and requires a lot of boilerplate, and we have computers to do that for us, so that's what this is about. Okay, so the package I'm talking about here is called statsmodels.jl, and this package, in my opinion, one of the main things that this package provides is the formula macro, which is a domain-specific language that provides high-level specifications of table-to-matrix transformations. And in the past, in the distant past, this is borrowed basically from R. Right? So if you have done any R coding and run regression models in R or any other sort of analysis in R, you're familiar with this language. It's tildes. And in the past in Julia, this was part of the data frames package. And I think the motivation for including it there is that data frames was the tabular data store for Julia for a long time. And the downside is that in the master branch still, and historically, it's hard-coded to use data frames. Right? So if you have some of the tabular data store, like a named tuple of columns or a JuliaDB or something like that, you can't use this. It was hard to extend, and the expressions that the formula macro understood were limited to the domain-specific language expressions. So any other normal Julia code would just choke. Okay, so the future is bright. The plan is to have it be totally back-end agnostic, and this is possible now that we have named tuples in base. That makes it very easy to kind of have a common data interchange format. For the language to be extensible at multiple stages, so it's easy for package authors who, let's say you have a specialized sort of statistical method and you need something other than just the vanilla formula DSL. Easy to extend, and that most importantly, that you can put arbitrary Julia code inside the formula expressions and just have it work magically. And this is really important to deal with streaming data, because historically, say, okay, let's say you want to log transform a variable, right? You can't just say log a variable in the formula. You have to actually put a column in your data frame that is the log transform of that variable, right? That's great if you have data that's in memory, but if you want to run some sort of streaming analysis, that's garbage, right? You have to write some other transformer that sits in between the data and the model, and that's not good, right? So we want to support sort of generic transformations in the formula. Okay, and I'll say the present is this pull request on stats model. So if you want to follow along, you have to go and check out this pull request. Okay. It includes all these features, it's not fully tested, and it's a little janky in some places, but I think it has a good heart, right? Okay, so the plan for the talk is I'm going to talk about first, what is the formula language? I'm going to sort of blaze quickly through how it actually is implemented, and then I'll talk about how you can build on top of it in your own packages. So the formula language is for organizing and transforming tabular data. Okay, and the basic structure of the organization is that you're separating response variables and predictor variables to put into, say, a regression model, right? So if you want to run a regression that is modeling y as a function of a, where y and a are columns in your tabular data store, your formula looks like this. And the tilde is the thing that separates the response from the predictor. Okay, and you can combine multiple predictors with a plus right? So this says I want to run a regression, or I want to generate a numerical matrix where I pull out columns A and B and smash them together somehow to make a single matrix that I can put as a predictor into, say, a regression model. Okay, you can also do these sort of transformations where you, let's say you want to model not only the independent effects of A and B, but also how let's say the effect of A, the slope of A in your regression model varies as a function of B, right? And that's with the ampersand. So if you're used to R, this is the colon in R is the ampersand in the Julia formula language. Okay, and there's a shorthand here where if, like me, you're including a large number of predictors, and you want to fit all of the main effects, all the individual effects, plus all the interactions. You can use the star operator. And the formula will generate a model matrix that has a column for columns A and columns B, and the columns for the interaction terms. Okay, now the really cool thing that you might want to do that's new in this, what I'm talking about here, is sort of arbitrary element-wise, or arbitrary Julia functions that are applied element-wise to the columns pulled out of the data table. Right. So this will just log transform A and generate a predictor for it. Okay. And also you might want to do sort of other specialized transformations. These are things that are not implemented in stats models JL, even in terms 2 son of terms. They're things that you package authors, like if you have a mixed effects regression package, could build on top of the language I'm going to talk about. Or you'll say you want to do like a B-spline regression, right? A nonlinear regression. Okay, so that's the sort of the basic outline of what the language is. Now let's talk about how we actually implement it in Julia. And this is the innovation in sort of the next generation formula language, terms 2 son of terms. So there's sort of 3 stages here, and each stage does something distinct, and each stage is customizable and individually composable, right? So there's a macro time stage, which is just transformations of the surface syntax, just based on the expression. There's a schema time, where you specify and extract the information from the data store that's the invariance about the data that you need to actually generate a numerical matrix based on the table. So like categorical versus continuous variables, levels of categorical variables, things like that. And then there's a data time or runtime where you actually have a complete data table, or you have a row from a data table. Okay, so first, macro time. So a macro gets a surface syntax from Julia in the form of an expression, right? So here is an expression, y tilde 1 plus a star b, right? And the first thing that it does is it has this parse function that just rewrites that in place, right? So the star gets expanded to a plus b plus a and b. Here. There's like a distributive rule that it applies. So if you want to like do two-way interactions between a and b and c and d, but not the interaction of a and b or c and d, you can do that. It'll distribute the ampersand, the interaction across those 2 sums. Okay, and then finally, this terms exclamation point wraps all of the symbols in constructors to a term struct, which is a sort of internal kind of placeholder, lazy marker for a column that you will eventually pull out of your tabular data store. Right? So now at the end here, we just have an expression that's just these term objects as arguments to normal Julia operators, right? Okay. Okay, so remember what a macro does. A macro takes one expression, transforms it to another expression, and then immediately compiles and evaluates that code, right? Okay, so this is if you just use macro expand to introspect what the formula macro is doing, it's doing exactly what I just showed you, right? Parses the expression to generate a lowered expression, and then wraps everything in terms, and then evaluates that. Okay, and what stats models JL, terms 2 son of terms, provides is methods for the DSL operators for subtypes of this abstract term. Okay, so if you add 2 term objects together, you get a tuple of terms. And if you give them as arguments to the little and function, you get a higher order term, which I call an interaction term, right? That again, it just has a tuple. It just sticks the tuple of those two terms in there, right? So again, these are all just sort of placeholders. We're sort of building up a lazy expression for how to actually evaluate this with respect to data later. And finally, the tilde operator just gives you a formula term, right? So if you're familiar with the kind of the old school original stats models formula language, this is the formula struct. There is no formula, right? A formula is, in this case, is just a term, right? A formula is a special kind of term that has a left-hand side and the right-hand side, right? And you'll see why that's powerful and important later. Okay, now, just an aside, how do we handle things that are not, calls to functions in the expression that are not part of the DSL, right? And so the first thing is that a call to a function like log that doesn't have a special meaning in the formula DSL, they block the DSL rewrites during the parse stage, right? So here the A star B here is expanded as before, but inside the log it's not, right? So everything, as soon as you hit a call that's not part of the DSL, you just stop the parsing, okay? The second thing is it lowers to, at the term stage, a call to this function capture call, right? Which gives you it's going to give you, when you evaluate this, the actual function that you would have called if this was just normal vanilla Julia code. It's going to give you an anonymous function that maps the symbol, every symbol that it found here, it becomes one argument in the anonymous function, and it just wraps the expression that it found in that anonymous function. It gives you the names of the symbols that it extracted, and then it also gives you a quoted expression of the call that it actually, of the expression that it actually found. And this is really powerful because then it lets you actually intercept calls to particular functions, right? Because this is going to dispatch on the type of the function that it found, right? So if you want in your package handle the log function especially, you can intercept it here. You can also, I'll show you in a second, tell stats models that log is a special function as far as you're now concerned, right? And that'll, and then it will behave like any other function. It'll behave like plus or whatever, and create terms and expand the star and all that stuff. Okay. Okay, so that's macro time, right? So we take one surface syntax expression and generate another one that's a expression involving a bunch of terms. Okay, now what do we do at schema time? So there are two basic kinds of variables, right? There's a continuous variable, which basically is just a numeric array already, right? In which case we just sort of want to convert it over. Yeah, and there are categorical variables, like things like vectors of strings or symbols or anything that can't just be straightforwardly converted into a vector or an array of numbers, right? And categorical variables need to be encoded, right? So if you're familiar with ML stuff, you might call that one-hot coding, right? If you're familiar with regression, you might talk about contrast coding, where you generate sort of, instead of just like dummy variables, you can generate columns that represent certain average responses relative to certain baseline levels, things like that, right? And the encoding actually depends on, in order to fully specify how to do that encoding, you need to know what the unique values are for that variable, right? Because we want to have a portable thing that we can carry around and say, given some data that follows the schema, convert it into a numerical matrix. So in order to do that portably, you need to actually, not just know the type, but you need to know what the unique values are, say, for categorical variables. Okay, and a schema in this scheme captures all the necessary invariants to do these transformations. Okay, so this I just shamelessly stole from JuliaDB.ml. So a schema is just a dict that maps lazy terms, so unevaluated terms, to either a categorical term or a continuous term. And these terms are just structs that have an online stat series that has the information that you need to actually do the conversion. Again, I just stole that from this very nice setup they have in JuliaDB. So you can see that if I have data in the form of a named tuple of columns, right? So Y is just 10 random floats. A is a sampled from the range integers 1 to 3. B is some symbols, and I call schema on that. Then I will get term. So this actually is a pretty printed term that maps to a continuous term. B is a categorical that is going to generate 2 columns in the result that defaults to dummy coding. So that's like one-hot coding with one-hot coding, but you drop the first level. which is standard in regression modeling, because you standardly include an intercept term. And y maps to a continuous variable. Right? So you see that both the ints and the floats get mapped to continuous terms, and the symbol gets mapped to a categorical term. Okay. And you can override this, again, shamelessly stolen from JuliaDB. You can override that with a dictionary of hints, right? So let's say I want to treat A as a categorical term, but I want to use a different contrast coding scheme for the B term. And don't worry if you don't know what this is. This is like a regression thing. If you know regression, you probably know what this means, but otherwise not. And here we get a different schema, right? Okay. Now, once you have a schema, you can apply it to a formula term or any term or tuple of terms, and it will just go through and it'll create a new copy of that term with the unevaluated terms that it finds at leaf nodes in that term tree, replaced with the items from this entries from the schema. Right. So here it's gone through and replaced, the y term with the y continuous term. And actually, these continuous terms, they have like, right now I just have it just tracks the mean and the variance of the column, right? But you could have it track you could put in the series to track the extreme values, things like that. Right. And it's replaced b with this categorical term. So that's the apply schema function. So you extract a schema with schema, you apply it to a term with apply schema. Okay. And there are, this apply schema dispatches on the last argument, so you can actually, if you want to sort of apply the schema in a smarter way, you can wrap that schema dict in another struct, or create your own kind of schema types, right? So a common thing in regression modeling is that you might, commonly you want to include a constant intercept term, right, in your design matrix, which lets you fit a regression coefficient that's just like the grand mean of everything, right? Or some baseline, the mean effect, the mean value of y at some baseline level, right? And if you code your categorical variables so let's say, so B has 3 levels, right? It has its 3 different symbols. If you create a 3-column, one-hot coded version of B, those 3 columns are linearly equivalent to the intercept to the constant column, right? And so you don't want to make up when you include an intercept term, you don't want to generate all 3 columns, right? Because you're going to get a rank deficient model matrix. It has 4 columns, but really it has 3 linear independent columns, right? But when you don't include the intercept term, if you only generated 2 model matrix columns, you're actually sort of doing a kind of ill-defined regression problem, because you're assuming that the average value for y is going to be exactly 0 at whatever the baseline level of that categorical variable is. And so in that case, you actually want to promote the coding of B to full dummy coding or one-hot encoding, where you actually generate 3 columns, right? And so so if you wrap the schema in this full rank wrapper, it'll do that check for you. And this applies, the same logic applies at higher levels. So like, let's say you have an interaction with B without the main effect of whatever the variable is that B is interacting with. In that case, you also need to promote, because otherwise you're going to get a kind of similarly ill-posed problem. Anyway, that's just a little bit of regression ephemera. Okay, now the fun part, we have data. We want to apply our schema to the data. Okay, or we want to generate model matrix columns from the data. Okay, so now we have this formula F, where we've applied the schema from the data to the formula. This is a formula that has now typed schematized terms as its leaf nodes, right? So let's say we have a data table that looks like this, right? So I've just pretty printed the named tuple of columns, and this is what happens if we generate model columns from this formula according to that data. Right? As you can see that it's generated 1 column that's a constant 1s based on the intercept term, and then it's just pulled out the A column from here and turned it into floats. So now we have a float matrix. And the reason you need to say last here is that this actually generates a tuple of the response vector and the predictor matrix. Okay. And if we include a term for B now, it's going to generate, 2 columns for B, right? So it's probably decided that B is the base level of this variable because it's the one that it saw first. Right, so you see that it's generating zeros for B. When it hits an A, it generates a 1. When it hits a C, it generates a 1 in the second column. Okay. So now we've taken a table and turned it into a matrix that we can put into our regression analysis. Right? This is the end of the pipeline. Okay. Now, you need a formula, right? You can do the same thing for a single term, right? So I can create a single term. Now, this is no macro magic, right? This is all standard runtime Julia stuff. You can create a single term for the B, apply a schema to it, and generate model columns for it. So this design is much more composable than it used to be if you're used to the old formula setup. Okay. And you can verify that the columns that it generates are the same if generating them alone. Okay. Right. Now, here to show you that any of the calls that it finds that are not special get evaluated element-wise. Right? So here I have a log of a and a squared, and you can see that I get a, the log of a, and values in a squared. So this supports arbitrary Julia functions applied element-wise to the column. Summary data. Okay. And it also works with a single row, right? So I now have just manually specified a named tuple of y, a, and b, and it generates the value, it pulls out the value of y for the first element in model calls, and a vector for the predictor on the right side. Okay, and the important thing here is that all you need to do this is the schema, right? And so if you have truly streaming data, you actually have to go and consume the data to get the schema if you don't know what it is ahead of time. If you know what it is ahead of time, you can just specify the schema yourself, right? The schema is just a dict of terms to typed schematized terms. Okay, great. So that's how it works inside, and just sort of a quick run through of what it can do. Okay, so now let's say you're like, boring. My modeling is way more sophisticated than this garbage, right? So I'm going to show you quickly in the last two or three minutes how you can intercept this and actually generate fully custom behavior building on top of this system. Okay, and the important thing is you actually can interject custom behavior at every single one of these stages, right? So you can interject it at macro time, at schema time, and at data time. Okay, 4 minutes. Okay. So here's an example. Let's say we want to do like a polynomial regression. Right? So the first thing you do is you'd find a term type. There's a subtype of abstract term that's going to hold the information that you need to actually generate predictors for this new type of regression. Right? So it's going to hold the term that corresponds to like the term you want to generate polynomial functions of, and the degree of the polynomial. This is like I want to just sort of compactly specify I want x squared, x cubed, x4, x5 as columns in my design matrix. Okay, so the first most obvious approach is you set this is special flag for the value for a val type of the symbol you want the formula to consider to be a special call to be true. Right? Because this is what that parse function is checking, right? To know whether to descend into the AST to generate terms, right? And then you specify a method for your function that takes a term as an argument and generates your special term. Now, unfortunately, this doesn't work in my sort of quickly hacked together version because of the way that numbers are handled in formula expressions, where I just assumed that any number you see is you're going to want it to be an intercept term or a non-intercept term, right? And that's fixable, but it doesn't work right now. The second approach is you actually use capture call to intercept at runtime to intercept calls to this function. Right? So remember, capture call gets the function that would have been called. So we're dispatching on type of poly, where now poly is a function that you have to actually define somewhere, even if it's just an empty stub. We're just going to ignore the anonymous function in the names, and we're actually going to directly work with the expression AST that was pulled out of the formula, right? And so in this AST, the first arg is going to be poly, the call, the function that was called. The second arg is going to be the symbol, right, which we're going to wrap in, oh, I got the parentheses wrong here. We're going to wrap in a term, and then we're going to pass the third argument as the degree of the polynomial to the constructor of our special term type. Okay. And at schema time, you have to tell stats models that you want to generate a schema for the term that's contained in your special struct, and then tell it how to apply a schema to your special struct, right? So here we're just generating a new poly term where we apply the schema to the term where we've wrapped and just pass the degree on through. And finally, at data time, you just have to define a method for model calls that takes a named tuple of data and your term. And all we're doing here is we're generating the column you would generate for that term based on the data, and then we're just going to splat together the columns raised element-wise to the appropriate power. And it's important to use broadcast in here because you might get a scalar or you might get a vector, right? Because you might get a single row or you might get a table, which is a named tuple of columns. So yeah, broadcast is actually the thing that makes this whole thing really easy to do. Okay, and here just to show you that it works. I have a live demo too, but I think I won't have time for it. Right? But so here's our special syntax. And here's to show you that we get, so polyterm, now the schema has been applied to the term contained inside the polyterm, and the int has just been passed through. And when we generate the actual model matrix, we get 3 columns, right? Here's A squared, A cubed. Okay. I think I'll skip this in the interest of time. This was my original example, but actually the polyterm one I think is nicer. Okay, just to wrap up really quickly. Statsmodels.jl terms to son of terms provides the formula DSL to transform your tabular data into numerical matrix suitable for modeling, right? And in working on this, I've been really pleased with to discover how easy some of the central features of Julia make it to do this in a way that's both composable and performant, right? So we have multiple dispatch generic functions, which lets us dispatch on these term types, right? Fast anonymous functions, which is the critical thing for allowing these sort of arbitrary transformations, right? And named tuples is a really convenient sort of lowest common denominator of like a heterogeneously typed named data store, right? Okay, I just want to thank Doug Bates in particular for doing a lot of the original work on the formulas in Julia, and the other contributors to the Julia Stats organization, and also my home for the last couple of years while I was working on this, and my source of my funding for that time too. And thank you for listening.
Thanks, Dave. This is really exciting work. I'm excited to go use it immediately. And we have time for questions, or if we all vote, we can see the live demo to really put the screws to it.
So for the streaming stuff, can you pre-allocate a buffer vector so that your things keep repopulating the same thing as opposed to generating a new vector at each observation?
In principle, yes. At the moment, no. Yeah. So the plan is so the question was whether you can whether you're actually going to reallocate a new vector every time you call that model calls function. So the plan is to have model calls with an exclamation point, right? So you can write it and that's really critical actually for actually even generating based on a in-memory table efficiently, because you don't want to allocate all these matrices and then glom them together, which is the current strategy, which is easy to write and it's not very performant, right? But yeah.
On a related note, my question was, can you output things other than array?
Yeah, that's a great question. I mean, there's nothing stopping you, right? You need to be careful about, So yeah, you can always write your own function that takes terms, right, and data and generates things, right?
Okay.
So this is just sort of like yeah, you can generate you can do anything that will allow you to that supports like catting, right? Because the way it works is that it
Oh, the
broad-
HCATs.
yeah, it broadcasts down to all the leaf nodes and then cats them together, right? But again, you could write your own custom
CUDA array
methods or
version.
wrapper, yeah.
Someone needs to, not me, but somebody else, needs to write making models on the GPU.
Yeah, right, exactly. Yeah.
In the past, in the data frame API, it used to be possible where you would create a formula and you would pass that to a data frame and you would get a model frame as your return type. And then from a model frame, you could build a model matrix or either a dense model matrix or a sparse model matrix. Yeah. Does that all still flow together nicely in this extension of formula?
Yes, so in terms, two set of terms, I have preserved the model frame API. So the model frame API at a high level in model matrix works. So you can pass a matrix type. It's not guaranteed to be particularly performant at the moment, right? But for now, that API still works, yeah. And the model frame, I don't think is necessary now that the formula carries around all the information you need to do the transformation, right? Because historically, what a model frame was a data frame plus a formula that had been parsed into some internal representation that would allow you to actually generate a matrix, right? But now the formula is its own matrix generator once the schema has been applied to it, right? So the innards of the model frame struct have changed in this pull request, right? But it's still there, yeah.
How do you manage the ambiguity between for plus and star between REPL writing and linear model or DSL writing?
Can you say the last part of that again? The first.
For instance, if I want to regress on the variable a plus b, but the sum of them.
Oh yeah.
How would you manage this ambiguity?
Yeah. So I don't at the moment. I just assume that plus, when it occurs in the DSL, is concatenation. I think what we really need is some sort of quoting, right? So in theory, you could you could define a special function that's like that just as an identity. Actually, you maybe even could put identity around a plus b, and that might actually work off the shelf. That's maybe a good question for the live demo, but I don't know. Yeah. So, but that's pretty verbose. I think you could probably use you could even define an alias, say const capital I. Well, capital I is not available anymore, right? But ID or whatever, right? But yeah. So you'd have to wrap it in something, yeah, to block the DSL application. Yeah.
Any other questions? Okay, we'll thank Dave again.